In this module, we'll look at magnetic force on a current carrying wire. So we'll look at magnetic force on the current as opposed to magnetic force on the moving charge. If you recall, our Hall effect, if we had current flowing downward in a copper conductor or any type of conductor, then we have conduction electrons moving upward. If this magnetic field was pointing, the X presents magnetic field pointing into the page. Then if we do our right-hand rule, so in this case we have, since our magnetic force is Q V crossed B, we could use our right-hand rule on V cross B, point our right hand in the direction of V, curl in the direction of B, and our thumb would point in the direction of the force on a positive charge. If we want to find for negative E V cross B, that's then equal to E B crossed with V. So we could point our right hand in the direction of B, which is into the page, curl it in the direction of the velocity, and we find that the force on our negative charge is to the left. Well, similarly, if we had positive charge carriers, we could use our right-hand rule on V cross B, in that case, since our Q is positive, and our positive charge carriers would still be forced to the right. In both scenarios, the force is in the same direction. So it must be the case, then, that that force on these charge carriers should be transmitted to the wire. And if we have a current flowing down in this wire, we could actually see the wire move. And that's in fact true. It doesn't matter the force on the wire, we can't tell through the transverse voltage. If we don't measure that, we don't know whether the current carrier is negative or positive, but we see regardless if our current's flowing downward, we're going to get a force on the wire. And again, you can prove it to yourself, whether we have a negative charge drifting in the opposite direction of the current flow or a positive charge moving in the direction of the current flow. So I recommend that you pause this video and prove to yourself as soon as this current's turned on, whether it's positive charge flowing upward or negative charge flowing downward, the force on the charge carrier will be to the right. And you can use your right-hand rule to prove that, right-hand rule associated with the cross product. If we reverse the direction of the current flow, if the current instead of flowing upward flows downward and the magnetic field is still out of the page shown by this dot, then that's going to reverse the direction of the force on the wire. Again, pause the video and prove to yourself with the right-hand rule that you can show that that will be the direction of the force on the charge carrier. If we reverse the poles of the magnet, if instead of having the magnetic field pointing towards us, the magnetic field is pointing away and into the page, currents in both scenarios are flowing upward, we have an opposite direction of the force on the wire. So the question is, can we relate that magnetic force to the current in the wire instead of to the velocity of the charge carriers? So our formula, our Q, V cross B, where V is the velocity, the drift speed of the charge carriers, can we relate it to the current instead? Well, one of our issues with current is current, although it has a direction, it's not a vector. So we can't do a cross product on a scalar quantity. We can only do a cross product on a vector quantity. So if we consider, for example, a length of wire L, in this case we show a current flowing upward and a magnetic field pointing towards us, we could find the magnitude of that magnetic force using our Q VB assigned phi. In this case, our phi would be 90 degrees. The drift speed of our electrons is in the perpendicular direction of the magnetic field. So we have our magnetic field is perpendicular to the drift speed. Well, we can relate Q to I. We can relate Q to the current. Q is the integral of I dt. If our I is constant, we have a constant current, then that we can pull I out of the integral and we just get I times our change in time, or net change in time, is that the amount of time it takes for the current to travel will be L divided by the drift speed. So we can then take our formula, QV drift speed, B sine phi, and substitute in for our Q, our IL over VD, and the drift speed cancels, and we end up with a magnetic force of ILB, where again L is the length of the segment of wire that we're looking to find a force on, but the reason we can do our cross product there is because the direction of L has a magnitude is equal to L. The direction is the direction of I, even though I is not a vector. So that's the magnitude of our force. If our magnetic field is not perpendicular to the wire, then the magnitude of our force is our ILB sine of phi, whatever that angle is, that relative angle between the wire and the magnetic field. They don't have to be perpendicular. What has to be perpendicular is the magnetic force. So our force on the wire as opposed to our force on a moving charge, where again L, our vector L is a wire segment that points in the direction of the current I. So generally, we prefer to use this first equation to define the magnetic field, as it's much easier to measure the force on the wire than it is to measure the force on the moving charge if we're trying to find magnetic field due to current flowing through the wire. If the wire is not straight, or if the magnetic field is not uniform, we can still imagine the wire broken up into small sections, and our differential force at any point on the wire is going to be I times that small length of wire, where we can say it has a same direction. And of course our wire will all have the same current I flowing through it. And we can do a cross product there. If we wanted to find the total force, then we could integrate over these two. We might have to break up our integral. If it is a we have a segment of wire that in fact has the same current. If we're going, for example, from B to A, that's B and that's A, we can integrate over that length of wire there. And as an example, if our magnetic field is uniform, well, if it's uniform, then we can pull it out of the integral, but we still have to do a cross product of it. But we're doing our integral from B to A of our ds segment of that movement of the charge, or movement of the current, which is the movement of the charge. But that integral from B to A, that's going to be this length L here. So our magnetic force is still our IL crossed B. If we look here, this segment of current seems to be going in the same direction of the magnetic field. So the force on this segment of wire will be close to zero. The force on this segment of wire will still be perpendicular to both the magnetic field, we can do it with our right-hand rule, and perpendicular to the current. So it will point, we do our right-hand curl there, or point into the page, but the total magnetic force, the magnitude of magnetic force, will be our ILB sine phi if we sum up the force on the total wire. Where's our phi, right? So there's our phi right there, relative to this length L. If we have a uniform magnetic field and we also have a closed loop of wire, then our integral from B to A becomes our closed integral of ds. We're integrating from whatever this point A back to point A again. That gives us the closed integral. Well, the closed integral around the loop is just going to be zero, because remember, it's a vector, right? So it's a vector. So even though we're changing direction, so for example, this might be positive, but over here that's negative, they'll cancel. The closed integral of ds vector is zero. So let's look at another example here. This figure shows current I flowing through this segment of wire in a uniform magnetic field, not shown, but we are shown the magnetic force acting on the wire. And we'll make a check here. Is in fact our current is flowing in the negative x direction, our force in the positive z direction. So they are perpendicular, and that's important because that must be true, because we know our FB is equal to our I L cross B, where L is the direction of our length L. Then it's going to be, there's L, our L vector, and it's from here to there, pointing in that direction. It's a vector. Okay, so what we want to find then is the magnetic field, but we're also given the information that the field is oriented so that the force is a maximum. So if we want the force to be a maximum, that tells us that L, well, magnitude of L, magnitude of B, sine phi must be a maximum. So that means that L is perpendicular to B. So we know our magnetic field is going to point in either the positive y direction or negative y direction, and we can use our right-hand rule to determine if, in order to get point our fingers in the direction of I, curl in the direction of B, we want our thumb to point in the positive z direction, then our magnetic field must be pointing in the negative y direction. Let's look at one more example. If we have a wire that's, we know the length of the wire, we know it's carrying a current of 13 amps, and it makes an angle of 35 degrees with a uniform magnetic field, and we know the magnitude of that is 1.5 teslas. And we want to calculate the magnetic force on the wire. Well, how are we going to draw a diagram? Where can we get a uniform magnetic field? We can get a uniform magnetic field between two opposite poles of a magnet. The magnetic field points away from the north pole of the magnet toward the south pole of the magnet. And if we have a current then flowing, we have a current flowing through a wire here, we can show that current flowing in this segment. So the length of our wire will be from here to here that we're considering, and our L vector points in the direction of the current. That's the direction of the current. And here's our phi, and this is our magnetic field. So if we want to do this calculation, then we've labeled our diagram. We have our length vector, we have our current variable, we have phi, we have magnetic field, we have all those given specified to 3 significant digits. We want to know what's the magnitude of the magnetic force. So our theory then, we can use our I, L cross B. That's what our vector is. So the magnitude of our vector FB is our ILB sine our phi 35 degrees. We can plug in for that, and we find that that's 20.1 newtons, expressing our answer to 3 significant digits as our givens are. Let's look at one last example here of a loudspeaker, which is an example of using magnetic field with current flowing through a wire. So we have current flowing through this coil here, and that current is carrying the sound. So our current is carried, our sound is carried, it's converted to electrical current, and it's carried sinusoidally at different frequencies. So what's going to happen here is, as the current flows through here for the North Pole, we have a magnetic field pointing in this direction. So we're going to have a force on our wire. These aren't quite closed loops, they coil around, and depending upon the direction of the current, the force on the wires are either going to be outward, pulling the coil out, or inward, pulling the coil in. And as the coil goes in and out and in and out, well, that causes pressure waves, and those pressure waves then are extended to the speaker cone, and that's what converts that electrical signal back to sound. So within one sound cycle, we reverse our current, direction of our current 2 times, right? So here we have positive current. Here we have, well, I guess it's still positive. In this section, we have positive current flowing in one direction. It turns around and flows in the other direction. So within each cycle, we reverse our current 2 times. So if we change the direction of the frequency 30 to 30,000 times, then we're going to produce a sound frequency of 15 to 15,000 hertz.